system. And if the motion is integrable, then you're guaranteed you're on a two-dimensional torus. Now, two-dimensional tori will foliate the space, will laminate. That is, if you have one torus, I'll do it in cross-section. If you got one torus which looks like this, and a bigger torus with a different energy which looks like that, etc., then a point inside cannot get out into the region between the two tori in a four-dimensional space. But for all n greater than or equal to 3, the phase space has at least 6 dimensions. The tori will have 3 dimensions, 4 dimensions, etc., n dimensions, and then they can escape in between. The tori do not laminate or foliate the space. And that means that if you start with an initial condition which is not in a region of phase space where the system is integrable, and there are such systems, they become partly chaotic, this irregular motion will permeate through all of available phase space sooner or later without crossing tori. And that's called Arnold diffusion. And it's very crucial in accelerator physics. When I talk about chaos, I'll come back and mention what happens there. Okay, now what I want to do is to say, okay, now that we understand the two-dimensional oscillator a little bit, let's look at a very special case of it. Yeah. If you don't have integrability, you cannot find action angle variables in which the system will become integral. That's right. You can still talk about action, you can talk about angle, you can write prescriptions for some of the variables, for instance, but the system will not be fully integral. Yeah, you can still do that, but it's useless. It doesn't help. It helps in the sense that if you're close to a perturbation to an integrable system, then yes, I would do it that way. And then I would perturb the system with a small portion of the Hamilton. That's how I do classical perturbation. So yes, indeed. So the Cam theorem and then things which follow from it would involve precisely that. So let me look now at a very special case, which is the 2D isotropic oscillator, because it gives you some valuable lessons about symmetry. Here I set the masses equal and the frequencies equal. So it's really like a particle attached to a spring, which is isotropic in all directions. And in suitable units, the Hamiltonian is 1/2 q1 squared plus p1 squared plus q2 squared plus p2 squared. Now you come along and say, this is immediately integrable because q1 squared plus p1 squared is one constant of the motion. This guy is another constant of the motion. It's integrable. The two frequencies are equal to each other. So on that torus, when it goes around once like this, it also goes around once like this. So it's completely integrable. It is not quasi-periodic motion. It's commensurate motion. And if the two amplitudes are chosen to be the same, then the motion is on a circle. In the Q1, Q2 plane, it will be a circle. So it's completely trivial. Now the question is, what is the symmetry of this system? What's the dynamical symmetry? First, I have to define what's dynamical symmetry. And ask, does this problem seems to possess some extra symmetry? Because it looks like under rotations in the Q1, Q2, P1, P2 space, nothing happens. The Hamiltonian is unchanged. So, the dynamical symmetry of a Hamiltonian system, or for that matter any dynamical system, would be a set of transformations, a transformation such that the equations of motion don't change. And the equations of motion don't change, what does that imply? It does not imply that the solutions, each solution remains invariant. It implies that the set of solutions does not change. After all, if I give you this equation, x squared equal to 4, x equal to plus or minus 2, and I change variables to x goes to x prime equal to minus x, the equation does not change in form. It's x prime squared is 4, but the solution plus 2 goes to minus 2, minus 2 goes to plus 2. So the set of solutions is invariant. In other words, the solution space is invariant. Individual solutions will, of course, change. Just like in the case of magnetism, you have a magnet pointing in some direction. You start with the Hamiltonian that's rotationally invariant. If it develops a spontaneous magnetization, then rotational invariance is broken because one particular direction is singled out. The Hamiltonian is still invariant, I mean the system is still invariant under rotations about that special axis, but the only case where this thermodynamic equilibrium state of the system, which is appropriate when you look at the finite temperature, has the same symmetry as the free energy, is the null vector, zero magnetization. Because that's invariant just like the free energy is. On the other hand, below Tc, that's not true, and there's a special direction singled out, and you have broken symmetry. So the solution space is left unchanged. Even in the case when you have a magnetization, any two magnetizations are related to each other by a rotation transformation. So the set of possible directions is still left invariant. And of course, if you have an infinite number of degrees of freedom, you can connect one ground state to the other by an infinite number of Goldstone bosons, which cost no energy and will take you from one magnetization to another. And all the rest of it follows. But in this very simple instance of dynamical systems, we'd like to know what's the invariance group in this case. So first I know that in order to keep the equations of motion in Hamiltonian form, the transformations must be canonical transformations. No question about it. So it must belong to SP4R. Whatever set of transformations in Q1, Q2, P1, P2 you want to make, they must belong to SP4R, otherwise it's not a canonical transformation, and you don't even preserve Hamilton's equations of motion, even in form. Then, in order to have the same solution, you need to make transformations which leave the Hamiltonian unchanged in form. So the new variables, the Hamiltonian must look exactly like the old Hamiltonian. And what's that? That you can see by inspection here. It's a four-dimensional space, and you got this sum of the squares of these real variables. So what's the group of transformations in this four-dimensional space that leaves this form invariant? Rotations in 4 dimensions. And they form a group. And what's that group? SO4. So the Hamiltonian is invariant under some group G, which in this case happens to be equal to SO4. This is the invariance group of the Hamiltonian. That's the set of canonical transformations. And now, in order to leave the solution space unchanged, the transformations must be both canonical as well as leave the Hamiltonian unchanged. So in some sense, it must be the set of transformations which is the intersection of these two fellows. So we want really the symmetry group, the dynamical symmetry group of the system, G, is the intersection of SP4. Intersection, I must guarantee that it's a group and so on and so forth. So it must be this. It must be some subgroup of the symplectic group, definitely. It's a big group. So we need some subgroup. By the way, how many generators does this have? N is 2 here. So 2n plus 1 is 10. And then twice that. 2n plus 1 is 5, and then twice that is 10. Whereas SO4 has 6 generators. So in a sense, it's smaller group. But that's not our concern. We want to know what subgroup of this is also sitting inside SO4. Now you have to immediately understand that you may have canonical transformations which do not keep the form of the Hamiltonian unchanged. There's a very simple one here which we studied. If I go to action angle variables, that's guaranteed to be an SP4R transformation, but that leads into I1 plus I2. I put omega I2 to 1. This form is not the same as that form. They're linear and that's quadratic. You're stuck. So all canonical transformations are not necessarily those which keep the Hamiltonian's form unchanged. This fellow will not belong to SO4. On the other hand, there are rotations in this phase space which will not be canonical transformations. Here's an example. Suppose you rotate in the Q1 P2 space. I leave Q2 and P1 unchanged, and I rotate in Q1 P2 plane, in the Q1 P2 plane. So I put Q1 prime is Q1 cos gamma plus P2 sin gamma, and similarly for P2. It preserves, the determinant is 1. It preserves measure. But what will be screwed up? The Poisson brackets will be screwed up. The Poisson bracket will go. So here's a simple example when you have to have just so. Everything has to be just so. Otherwise it's not true. So I give you an example of a canonical transformation which doesn't belong to SO4. And the transformation belongs to SO4 but is unfortunately not canonical. So you need to find the maximal subgroup of SP4R, which is sitting here, which intersects with SO4, and this portion must have a subgroup. That's the dynamical symmetry group of this symmetry. Its generators will be constants of the motion by Noether's theorem in classical mechanics. And we need to find these generators. They will form some algebra, which means they're not necessarily in involution with each other. And let's see explicitly what happens here. This group, by the way, in this problem it's known, this is equal to SUP. It's the same. It's isomorphic to the group of 2 by 2 unitary matrices with unit determinant. That's the dynamical symmetry group of the two-dimensional harmonic oscillator. Isotropic two-dimensional harmonic oscillator. It's also that then, you can ask a very tricky question here. Suppose you did quantum mechanics. Then the moment you have symmetry, extra symmetry like this isotropy, you also have degeneracy in the problem. Right? Immediately you have degeneracy. What's the degeneracy of the 2D oscillator? I quantize this guy, and then the energy levels are E as a function of two quantum numbers n1, n2 is h cross omega into n1 plus n2 plus 1, half for each of these guys. These are the quantum levels. Right? What's the degeneracy of all these guys? Well, that's easy to see because this is equal to some h cross omega into n plus 1, where n runs 0, 1, 2, 3, etc. And it's just the number of ways in which you can take a non-negative integer n and break it up into two non-negative integers n1 and n2. And what's that? The number of ways in which you can take n of these objects and put them in two boxes. Right? Yeah, n times n plus 1. Because there are n dots and 1 bar. So the number of permutations of these guys is n plus 1 factorial. But the balls are indistinguishable, the dots, so divide by n factorial. N plus 1. Okay. So the degeneracy Gn in this case equal to n plus 1. 2D isotropic. So symmetry implies degeneracy. What about the three-dimensional oscillator? Suppose I had one more, Q3 squared plus P3 squared, completely isotropic. Then this would be SP6, R. This symmetry group would be SO6. And again, you'd have to say what's the subgroup, maximal subgroup of this guy, which is also sitting inside SO6. What would your answer be? Your naive answer would be SU3 and you'd be right. So the n-dimensional isotropic harmonic oscillator, its dynamical symmetry group is SUN. How many generators does SUN have? N squared minus 1. The symplectic group itself has 2n squared plus n, and this guy is much smaller. It's n squared minus 1 generators. We'll come to this, the constants of the motion here. And what's the degeneracy? I mean, every time you do specific heat of solids and the Einstein model, and then you look at oscillators and so on, you're actually going to, you say there's oscillation in x direction, y direction, z direction, all have same frequency. Then you can compute the partition function by doing it in one dimension and cubing it. But you could also compute it by taking the quantum number n, putting in the degeneracy factor, and then summing over only one. Both are equal. So what's the degeneracy? Well, you have n objects and you want to break it up into 3 of these fellows. So you put 2 of these boxes, and this time it is n plus 2 factorial over 2 factorial n factorial. So that's the 3D. So you should try this. You put this Gn factor in and then do e to the minus beta h cross omega times n plus 3 halves, and you should get the same answer that you get by cubing the original sum without the degeneracy factor. So the important thing is that if you have n of them, the degeneracy goes like n. You can see that going like n to the power d minus 1. And that has to do with the density of states, or equal spaced. Alright, so coming back here, what's the generator of these SU2 of this guy? By Noether's theorem, we know that whatever generates this group SU2, they must be constants of the motion. So we got to discover constants of the motion here. We got one here, and we got another there. There are obviously other constants of the motion. They cannot be in involution because it's a 2-degree of freedom system, so the maximum 2 in involution. And we have a hint from the fact that they are generators of SU2. And you know that you can find the angular momentum algebra by taking 2 different harmonic oscillators and combining them. Playing this. Are you familiar with this way of finding the eigenvalues and eigenfunctions of angular momentum addition? If you have 2 oscillators, quantum oscillators, A dagger equal to B dagger equal to 1, like this, then you construct the operators A dagger A minus B dagger B, A dagger B plus A B dagger, apart from some factors, and then A dagger what's the third guy? What's the third guy's angular boson is angular momentum? Is it A dagger A plus B dagger B? Right. So you're going to get oh, okay. Okay, so well, let me write it in terms of J squared, J plus and J minus. So, or Jz, J plus, J minus. So you have A dagger A minus B dagger B, A B dagger, A dagger. These 3 guys will obey the algebra obeyed by J plus, J minus and Jz. And you can now write down what the J squared is in this language. It's A dagger A plus B dagger B, etc. And you can compute to find out all the eigenvalues of angular momentum, and you discover that J squared has eigenvalues J times, little j plus 1, where little j will be of the form 0, half, 1, 2, etc. So you discover both the fermions and the bosons, half value, half integer spin and integer spin. So that's what you go back and play with, and this is what will happen. So define J1 is, I remember the factors here, Q1 squared plus P1 squared minus Q2 squared minus P2 squared. J2 is 1 half Q1 Q2 plus P1 P2, and J3 equal to half angular momentum Q1 P2 minus Q2. Then it implies that the Poisson bracket of Ji with J equal to epsilon ijk, which is the angular momentum, which is also the algebra of SU2. As you know, SU2 is the universal covering group of SO3, and the Lie algebras are the same. I urge you to check as an exercise that each of these J's commutes with the Hamiltonian. Poisson commutes with the Hamiltonian. This is trivial because it's just F1 minus F2. But those two also. What's the significance of this in the isotropic oscillator? It's the arc angular momentum. If you look at it as motion on a plane, it's the angular momentum about the origin, which it will have to obey, be a constant of the motion because there is a central force. If the spring constants were different, it's no longer a central force. However, the SU2 symmetry persists if it's still a rational multiple. If omega 2 is a rational multiple of omega 1, the third integral of the motion is still isolating, it's more complicated. The spectrum is degenerate, it doesn't have degeneracy n plus 1, but the dynamical symmetry group is still SU2. And it's non-trivial to find the generators. Very non-trivial, reasonably non-trivial. So, what's the lesson here? The lesson is, you have many constants of the motion, but they're not all independent. Because look at what we've discovered. We got 4-dimensional phase space. There's 1, there's 2, there's 3, there's 4, there's 5. You can't have more than 3 of these guys, which are time independent and independent of each other. This one is obviously a difference of these two, so you can throw this out. But there's one more here. And that too, if you square, etc., is a function of the others. And there are indeed only 3 time independent constants of the motion. But they're not in involution with each other. And those guys definitely are not. They form a Lie algebra. But these two, or any two, suffice to make sure that the system is integrable and that this is a symmetry group, dynamical symmetry. Now, finding the dynamical symmetry group of an integrable system is not, again, non-trivial. Again, fairly non-trivial. For the case of, but the hint comes when you quantize and you find there's degeneracy, you know there's an extra symmetry present in the system. In the case of the Kepler problem, the 1 over R potential, the Hamiltonian, in that case, in 3 dimensions, is P squared over 2m minus some k over R, say attractive Kepler potential, say. Then the question is, what's the symmetry group of this guy? What's the dynamical symmetry group? Because I know it's integral. And I need 3 constants of the motion in involution with each other. What would you choose them to be? What's traditionally done when you do quantum mechanics, for example? What are the constants? What are the mutually commuting maximal set of commuting observables whose eigenvalues will label all the states of the system? N, L, and M. So it's clear that the Hamiltonian and then L squared and L squared, or any L dot n. These 3 guys are mutually in involution with each other, and that's the only number that you need, 3. Therefore, the system is guaranteed to be integral. And we immediately go to spherical polar coordinates, separate, etc., etc. But now this integrability, in the case of the Schrodinger equation, if you can solve this problem, this closed form, then it also implies that you have the possibility of, the moment you know it's fully integrable, you know that there are extra constants of the motion. N of them, for n degree of freedom system, there are n of them, other than the Galilean invariants. So there's an extra constants of the motion. And in this case, you know that the length vector E cross L minus n k r is also a constant of the motion. So now let me ask, we got 1, and then let's look at the angular momentum L. This is r cross p. So we got 1 plus 3, 4 plus 3, 7 constants of the motion in a phase space which is only 6-dimensional. And all 7 are time independent. So it's clear that you cannot have independence of all these things. Obvious that you won't, they're not all independent of each other. What's the maximum number that can be independent of each other? 5. It's a 6-dimensional phase space. 5 can be independent of each other. And indeed that's so, because you will take those 5, and by the way, all 5 will not be in involution with each other. What's the maximum number that can be in involution with each other? 3. H, L squared, and L z. That's one choice. Or L squared and any other component of L. Now, what are the functionally independent ones? We are familiar with these guys, so let's keep these. 1 plus 3, 4. Then 1 more must come from this length vector. By the way, it's a nice simple exercise to show that dA over dt is identically 0. So I urge you to do that. Use the equation of motion and show that dA over dt is 0. Sure. that out of this A, there must be only one functionally independent constant, not more than that. But you can see at once that this is so because A dot L is equal to 0, identical. You dot it with L, this goes away, and L is perpendicular to R, so that goes away. So A dot L is 0, which means the component of A perpendicular to the plane of the orbit is 0. A lies in the plane of the orbit, so in a sense it has only two independent components. Moreover, the magnitude of A can be fixed by the magnitude of L and H, by the energy and the total angular moment. So that's one more gone, and therefore you have only one left, which gives you your 5 constants of the motion, independent of each other, functionally independent of each other, or the differentials are linearly independent of each other. Now, the next question is, all right, once we know this, what about the quantum problem? What's going to happen? Well, the hydrogen atom problem has energy levels which would normally depend on N, L, and M. This M is different from that M. But, now it's a central force, and the central force has axial symmetry, certainly spherical symmetry in the potential. So no single direction can be singled out, no special direction can be singled out, which means this cannot happen for any central force. In the case of the hydrogen atom, it's a Kepler problem. It's super integrable in the sense that it has more constants of the motion than are needed than the Galilean integrals of the motion. There's hidden symmetry in the problem. And there's this extra vector constant of the motion. Right? So this implies that there is no dependence on L either. This is accidental symmetry, what you learn is accidental symmetry. That degeneracy arises because this problem is integral completely. There's many more constants of the motion. What's the algebra? What's the symmetry group? In this case, if you just look at this Hamiltonian and ask, what's the set of canonical transformations? It's again sp6r. That's a huge group. But you want all those things which are invariant, which leave the Hamiltonian invariant. Certainly rotations in physical space will leave the Hamiltonian invariant. So you might guess SO3. And you'll say, I'll go to spherical polar coordinates and also change the p theta, p phi, pr, etc. so that I have canonical transformations. And you'd guess, oh, SO3 is symmetrical. But this is some crazy potato-shaped object in 6-dimensional phase space. And you can't immediately tell me it's only rotations that will keep it invariant. Rotations in the coordinate space, which will keep it invariant. There's a bigger group of transformations which you can't detect from this. But the existence of that helps you to detect. This, from this vector and this vector, you can form combinations. You can find their commutators. By the way, what would this commutator be? Let's use elementary knowledge of quantum mechanics to do this. What would this be? Li, Lj. I'll use commutator or Poisson bracket into J. What would this be on the right hand side? It's angular momentum. Epsilon ijk k Lk. What would this be? Li Aj or minus it. What would this be? Apart from some sign and all that, it will be epsilon ijk k. Why? A is a vector. A is a vector. Therefore, it must transform like vector. So with the rotation generator, it must show up as one more of itself. That's the whole point. That will ensure that e to the I L dot n theta or psi acting on A, e to the minus L dot n psi on this side will give you the new operator A, which is rotated. Like a vector, it will transform like a vector. So this is A, apart from some sign. And for the algebra to close, you must have AI, AJ, and this will be of the form LK or something. So they form a closed algebra. However, it's not any recognizable algebra, as you see, but you can form combinations from L and A, which will have a recognizable algebra. You can roughly form combinations which look like L plus or minus A, but you've got to be careful of the physical dimensions, because this guy here doesn't have his dimensions of angular momentum, that fellow has some crazy dimensions, he's got extra momentum. So you've got to divide by something or the other, which will depend on the energy, on the Hamiltonian itself, with which everything Poisson commutes, so there's no problem. So there's some square root of energy or h or something sitting here. And these guys, you call them two vectors m and n, they satisfy two angular momentum algebras. Mi, mj is epsilon ijk mk, ni, nj is epsilon